So this is regarding the shapes of molecules. We are trying to see the 3D shape of the molecule instead of its 2D shape that we draw on the paper. So I will not trouble you with the name of the theory. The VSEPR theory, you will know its name and why it's named like that later. For the time being, let's have a look at the electrons. The electrons can be bonded in the covalent bonds in different ways. So if you have a covalent bond between two atoms, let's say these atoms are carbon and hydrogen or whatever kind of atoms you want to bond. So the covalent bond, as we know, is made by sharing two different electrons, one from each atom. Sometimes the electrons are not shared, so there are extra atoms which are around the atom, extra electrons around the atom. So the electrons can be bonded, and we call it the bond pair, or it can be lone pair. These are non-bonded pairs. So in this molecule, I can see the carbon surrounded by 4 hydrogens. All the valency electrons of the carbon are used in making bonds with the carbon, with the hydrogens. So this carbon has 1, 2, 3, 4 valency electrons. It will use all of them to make the bonds with the hydrogen, and there is no electrons extra that will exist as lone pair. The hydrogen also has 1 electron that will be bonded with the carbon and no extra electrons. While in water, I have 2 different types of electrons. I have these electrons also in ammonia. So I have lone pair of electrons and I have bond pairs. So this is oxygen. It has this one known as lone pair, and this is a lone pair. They are not used in bonding, and the ones in black are the bond pairs. Let's imagine a bond between the beryllium atom and the chlorine atom. This is a bonding pair. Because these are electrons, so this pair of electrons has negative charge, and they will repel anything that has a negative charge also. So let's imagine another bond, for example, another bond between the Pe and another Cl. Because this bond has also electrons, so it's also negative. So these two are going to repel each other. The bonding pairs are going to repel each other. So the repulsion, if we imagine one of them is a black color and the other is a blue color, we will imagine that these two lines trying to get away from each other and forming a certain angle. So this is a 90-degree angle. That's not good because there is still repulsion between the two lines. And I want the repulsion to be minimal repulsion. This is the theory of the VSEPR theory. It depends on decreasing or minimalizing the repulsion between the pairs of electrons. So this is different angles that it can take, and apparently not all of them are okay. The only way that the repulsion will be minimized if the angle is 180 degrees. So the angle between this bond pair and bond pair is 180 degrees. And we'll explain in the exam saying that this is the minimum repulsion possible. We call this shape the linear shape, and it's called linear because it has a straight line shape. I can see here the central atom of the beryllium and 2 other atoms, chlorine atoms around it. So let's practice drawing the beryllium fluoride. Try to draw the number of bonding pairs of electrons in each, the number of lone pair of electrons, then draw the diagram of the shape of the molecule, including lone pairs and bond angles. You can also try to name the shape. You can also do this practice on the HCN. Let me give you a hint about the HCN. This HCN will be drawn like that. This is the hydrogen, and it's bonded to 1 carbon, and then there is a triple bond with the other nitrogen. Try also to know the number of bonding pairs, the number of lone pairs, draw the diagram, and then the name of the shape. You can see that this repulsion occurs between electron pairs in the valency shell. So this repulsion is not shown in electrons in the lower energy shells, only in the valency shell electrons. As we agreed, we have lone pairs and bond pairs. There is also repulsion between the lone pair and bond pair. So I can see a repulsion here. this repulsion will be between these blue electrons, the blue circles, representing the lone pair, and the straight line, the black one, which we represented with the bond pair. There is also repulsion between the two bond pairs. You can see a repulsion between this line and a repulsion between this line. This is two bond pairs. So I'll try to minimize the repulsion as much as I can, make them far from each other. This is an option because the angle might be 180 like the previous one. But let's know something first about the repulsion. We'll know that the repulsion between a bond pair and a lone pair is not like the repulsion between a bond pair and a bond pair. So let's imagine I have a lone pair of electrons, a bond pair of electrons, and another bond pair. They are both negative, so they are repelling each other. They are trying to get away from each other, like we said, so they take this straight line shape, like in the PeCl2 in the linear shape, try to get away from each other. And there is another type of repulsion that can happen between this lone pair of electrons and the bond pair. Let's see the example here. There is a repulsion between the blue and the black, and repulsion between this black and the other black. So let's know that the repulsion between the bond pair and the lone pair is stronger than the repulsion between the bond pair and bond pair. This will force the molecule to take a certain shape to minimize the repulsion. So there is a repulsion here. The first repulsion is between the lone pair of electrons, which I'm gonna do in red now, and the other lone pair, and the black bond pair. And there is also repulsion between the black ones, the black straight lines, which are the bond pair. So let's call the first repulsion number 1 and the second repulsion number 2. We said that the first repulsion between the lone pair and bond pair is stronger. So they are going to push the electrons of the bond pair down. And there is also repulsion between the bond pairs, which are going to push the electrons of the bond pair up. So I can have a pushing, I have pushing from up here due to the repulsion between these ones and the bond pair, and another repulsion going from down because of the repulsion between this bond pair and this bond pair. But which one is stronger? Is it the first one or the second one? Because the repulsion from the top is higher, the repulsion between this bond pair and lone pair and this bond pair and lone pair, so number 1 is stronger than number 2. This causes it to force it to the bottom, so it forces it down. So in this way, the repulsion between the lone pair, this lone pair and bond pair, is stronger than the repulsion between, and this also lone pair and bond pair is stronger than the repulsion between this bond pair and bond pair. So it takes this shape. If you draw the shape in a different form, like this oxygen, and this bond pair came to the up, so now you are saying that the repulsion is between this bond pair and this bond pair is stronger than the repulsion between this lone pair and bond pair and this lone pair and bond pair, which is wrong. So you cannot say like that, this shape is not correct. In this case, due to the repulsion of these shapes, I will form a new shape which is called nonlinear or bent or V-shaped. It has this V shape, which is in the draw, and we sometimes call it bent or nonlinear shape. This can happen in oxygen with the hydrogens, also in the sulfur and in selenium with the hydrogens, which means in H2S and H2SE, because all of them are in group 6. So this is the linear shape is 180, but the nonlinear shape, the angle is not going to be 180, 104.5, and you must memorize this value. So any central atoms that will have two atoms around it, plus 2 lone pair of electrons, two bonding pairs, and 2 lone pairs will be considered as a bent or nonlinear shape, and the angle of it will be 104.5. So try to practice with the H2S. Another example, try to make more practice so that you can draw it easily.